We've only got a short while to go this afternoon, so let's kick it off. You are all familiar with him, but I'd like to reintroduce Simon Lucey, who will speak on AI innovation in Australia and what's on the horizon. Simon.
Thank you, and apologies once again to have to listen to me a second time. But we've got some visual aids this time to sort of differentiate things. So I'm the director of the Australian Institute of Machine Learning, taking over after Anton Venenhengel, and I've sort of only really arrived here in Adelaide probably last year. So just a little bit about the Institute. Many people know about it, but it's a little bit noisy, the rankings at the moment, but depending on what day you look at it, we're second or third in computer vision in research globally. We've won a bunch of sort of different competitions in the space, in autonomous vehicles, in space. We're actually involved with the European Space Agency, some competitions there. Volkswagen, Cityscapes, a bunch of groups. And so I think you heard us bragging about AML in the last discussion with Anton. But one thing I wanted to talk about a little bit today was sort of, because the theme is sort of hype versus reality. So one thing I wanted to talk about a little bit was this whole idea about, well, what's going to be happening in AI? Where is AI at the moment? What problems can AI be easily applied to? And what problems does AI still struggle with? And I find in my role at AML, that's one of the big questions we have when we talk with industry. They really ask us sort of like, is my problem ready for the prime time? Can AI be easily applied? Or is it sort of a research thing, or can it be something that I really struggle with? So I've had a bit of experience in this area. I was lucky enough, as I was mentioning in the last discussion, to work for an autonomous car company called Argo AI for about 3.5 years. You can see an example of one of the cars driving around here. You see one of these peculiar sort of camera setups on top. They've got a bunch of cameras, like they call them ring cameras. So they've got a bunch of cameras forwards and backwards, and they have this strange dome that's sitting on top of the car, something called a LiDAR. And so a LiDAR basically is like a radar for light. It's just using time of flight, how long a laser takes to hit an object, come back, and it gives you a 3D estimate of sort of the world. Now, what's interesting is actually when you look at one of these vehicles, what it's basically doing is in real time, it's trying to measure things about the world. Actually, sure that this is here. And so, and as Anton was talking about, the main engine for this is computer vision. And it's really sort of transforming pixel intensities into semantic measurements. So rather than measurements of light, the AI can then convert it into sort of, well, there's a car here, it's traveling at this velocity, there's a pedestrian here traveling at this velocity. And then based on that, once you have those symbols, then you can rely on sort of more classical AI algorithms to sort of determine where it should be moving and how it should be working. And as we spoke about too, sort of this 2011 sort of like salient moment caused a big innovation. We spoke about AlexNet and sort of how ever since 2011 for various tasks, especially tasks like in computer vision where I have to detect an object, detect a vehicle, detect a person, detect a cat versus a dog, we have actually surpassed what humans can do. So that's sort of like really amazing. And we're increasingly seeing this. We saw in sort of popular press a couple of years ago, games like Go, computers again outperforming humans. But what's really interesting is people get almost drunk on this idea that AI is achieving human-like performance in a lot of applications. But what's really interesting is how they achieve that performance. So here I've got a graph, and as a geeky professor at the University of Adelaide, we love graphs because they're a great way of sort of like understanding data. So on the x-axis, we have the amount of training data. So basically, you can think of that as the number of files or just the sheer amount of storage you have on your server. And it's a log scale, okay? So it's not a linear scale, it's a log scale. And on the y-axis, we have performance. And the performance could be for object detection or some other task. And so what we know with AI, and hopefully most of you guys are aware of this term deep learning. So deep learning is basically the secret sauce of modern AI. And it's very much data-driven. And so that's why we have a lot of discussions about data and AI. And what's really interesting with it is the performance of a deep learning algorithm is fundamentally linked to the amount of data that you throw at it. But you can see the performance sort of only increases slightly as you add more and more data. So it's a logarithmic scale. So initially I get a big bang for my buck, but I need an order of magnitude more data to start inching my performance up. And so it's a real law of diminishing returns. And so I have to sometimes collect a huge amount of data to start matching performances of humans. But when you look at humans themselves, we do not learn like this. We do not need to look at terabytes of images to learn a task. We only need a couple of examples. And so one of the huge hurdles that I believe is facing the AI community at the moment is not how to make machines pass human performance, it's how to make machines learn like humans. Because only then can we actually apply AI to a much broader set of problems. Because at the moment, the problems that are being applied to are the problems that multinationals care about or that there's enough venture capital money around for. It's very hard for SMEs to come up with an innovative idea in AI that only they care about and have enough data and compute to have a breakthrough. So it's a massive issue. So one example, hands up here, who's heard of GPT-3? Okay. That's okay, it's a disproportionate on that side versus that side. So GPT-3 hit the popular press probably about 12 months ago. It's probably, it was developed by OpenAI. It's probably the leading natural language processing model in the world. And it can do some astonishing things. You can just sort of list it off to do a couple of tasks and it can create HTML code for you. It can write essays. It can do all these amazing things. But it's so innovative. But one of the issues with it is that just say you had the data and you were a small company and you wanted to actually train that model up and change it and innovate it yourself. On a cloud, say on Amazon, you would actually have to pay $4.6 million just to train that model. Okay? So that's not your budget for hiring people. That's not your budget for innovating. That's how much it would cost for a private citizen to train that model. So completely outside the grasp of the average citizen or a small SME. So this is acting as a massive barrier for innovation in AI. And in fact, some of the top AI conferences we go to, even in the university sector now, there are models being released that universities in Australia cannot train. We don't have the data or the compute. So that's a massive issue. So how do we move forward? So some other examples here. You're a teenager, only needs 75 hours behind the wheel to get a license. But modern autonomous vehicles are needing millions of miles and they're still not on the roads. So one of the big mission statements we have at the Institute is basically trying to kind of bridge this gap. And that's one of the big innovations that we're trying to bring about at IML and one of the big missions that we're trying to drive forward here in Australia to try to allow SMEs and middle powers like Australia to really innovate in AI, not just following what's happening in AI. And so we're trying to kind of push this envelope to trying to get modern deep learning to kind of up to this corner. So what's on the horizon? So I got asked to kind of talk about some of the things that are on the horizon. There are a couple of things that we're very good at the Institute and I think are really exciting and you can keep a watch on. One area in particular is something called geometric deep learning. So that's allowing AI to make 3D sense of the world. So you could do that with your phone or a raw sensor and being able to, in 3 dimensions, understand what's happening in the world. Natural language processing, that is huge. In the last 12 to 24 months, that has been sort of really driving the field of AI, and there's a lot of innovation coming out in that space. Robotics. Robotics, especially in Australia, for logistics, there's a lot of work that's been going on in there. Advanced learning and reasoning. So at AML, I'm proud to say that we actually secured a large federal grant that actually Anton's the director of, the Centre for Augmented Reasoning, that we're kind of really driving forward some of these ideas over how we can kind of connect classical AI ideas in AI to modern machine learning. But one of the examples I want to kind of jump into a little bit here is geometric deep learning. What do I mean by that? So let's say I've got an image and I've just got these raw pixel intensities. Rather than just drawing boxes around them, can I actually determine exactly where the objects are in 3D? Just from the raw pixels. So the 3D structure, the surface, the position. That information is really, really important to us because just getting boxes on images is good, but if I want to actually navigate a robot or get a machine to move around, I need to know what's happening in the 3D world. So one of the sort of innovative things that are going on in the space is, and this is a brand new idea that's only come out in the last year, it's something called neural radiance fields. Many of you, I don't know anyone who's heard of neural radiance fields? All right, cool. All right, 2 people in the corner. We'll have a beer afterwards. Or NERF. And so the idea is really elegant. The idea is this. Let's say I have an image, and I have what we call a multi-layer perceptron. And I actually project a ray through my image, and I know that my 3D position of the object is somewhere along this ray. I call that 3D position X. And I feed that into my multi-layer perceptron. This multi-layer perceptron can actually output color and volume density. And what it does then is that we apply some fundamental ideas from physics. We integrate over that line and then basically reform the image. So it kind of conglomerates back there. Now, why this is cool is that I can apply this not just to one image, but to say, I don't know, 10 or 12 images, like on my phone. I've got my phone out, 10 or 12 images like this, right? And what I can do with this neural network is I can actually do something like this. I get an example of a couple of images, and I can stitch them all together. It can be any scene you like. And then I can actually interpolate any view from that, virtually. Now, what's really cool with this, and it's tying in to the narrative, is that there's no training data. I don't have to have a huge server farm to do this. I don't have to have millions of images. What we're working on here is some fundamental mathematics behind what's going on in neural networks themselves. And it's a really, really innovative idea. And what's it allowing us to do, too, is that we can actually get depth maps. And so it's allowing us to turn conventional phones and sensors into AI sensors. But the power of the idea is I don't need a huge amount of data. I could actually be a graduate student or a small SME using this technology, and I don't have to rely on a huge amounts of data or compute. Some other examples that we've sort of really excel at is tasks like sort of crowd counting and object counting. So obviously, if you ask a human, I've got a scene of a crowd like this, how many people are in the crowd? We would solve it in the way that humans would. We say, all right, I'm going to go through and count every person. Right? But AI doesn't need to necessarily solve it that way. I could present it with lots and lots of images of crowds, and it will find its own rules for counting. And what's really cool with that is oftentimes in crowds, you've got objects that are occluded, you've got people that are missing, and the neural network can actually do that very, very efficiently. So things like fruit, cells, people, and so we've got a lot of really innovative ideas in terms of how to do these types of tasks simply. Things like segmentation. So what part of a scene is the vehicle, what part of the scene is on the, is on the road, the sky, the background. And another thing that I'm proud to say at the University of Adelaide we're really world class on is something called vision and language. So if you were to ask someone in AI, what are the 2 areas of AI that are probably driving the field forward? It's computer vision and natural language processing. And so what's really cool is that at AML we've sort of innovated this brand new field called vision and language that connect the 2 together. So you can actually query images with text to find out what's in them. So you could kind of ask, sort of, you can query like, is there a man with a guitar in the scene? Or can I, so rather than actually just having to query things in text or vision, you can connect the 2 together, and it enables you to actually search and explore data in brand new ways. And that's really, really important too, as we're actually collecting more and more data and more and more rich types of data, working with these different modalities. And one of the big innovations in this field is something called transformer networks. So transformer networks are probably the big success story of the last 24 months in AI. And what's really powerful with them is it's a type of neural network, but it's a type of neural network that can be applied to nearly any data source. It can be applied equally to text, images, sounds, LiDAR, MRI, X-ray. And it doesn't matter what the modality of the data is. And what's really powerful with it is that you can mix the modalities and get it to learn from each other. And so that's a really, really innovative idea at the moment. Yeah, so basically that's sort of like my horizons, sort of what's happening on the field. Happy to field any questions, and thank you so much for your attention.